Today we're covering the identity matrix and then finding the inverse of a 2 by 2 matrix. Tomorrow we'll look at solving systems of equations using matrix equations. That involves finding an inverse, so it's kind of building on that. And that means next week, I know the schedule is going to be a little messed up because both sophomores and juniors have practice ACT tests on different days next week. So me teaching a class that has both sophomores and juniors in it just kind of messes things up. But the Chapter 3 test will be next week because we are finishing Chapter 3 tomorrow. So the earliest, I guess everybody planned for the Chapter 3 test to be on Wednesday. That's the earliest it would be. And then if it is pushed back at all, that just gives you extra time. But if you plan for it to be Wednesday, that's the earliest it would be. It would not be earlier or sooner than Wednesday. So you would start reviewing on Monday. That's the plan. So we'll talk more about that. I need to figure out with the change in schedule with sophomores and juniors for next week too. But the identity and inverse matrices for today, ultimately, we're going to be looking at determining if you're given two matrices, are they inverses, and then how you would find the inverse of a 2 by 2 matrix. So that's the ultimate goal at the end. And tomorrow we'll be building on that, finding the inverse to solve a matrix equation. But the identity matrix is a square matrix, so same number of rows as columns, that when multiplied by another matrix equals that same matrix. So basically, it's the equivalent of the number 1 in multiplication. When you multiply any number by 1, the number you started with doesn't change. That's the same for matrices with the identity matrix. If you take any matrix that's a square matrix and you multiply it by the identity matrix, it's not going to change the matrix you started with. You'll get that same matrix as your product. So this box, I'm going to kind of be looking between these two and then what's written here. But it explains the identity matrix for multiplication I. So the identity matrix, if you see capital I, that represents the identity matrix. And it is a square matrix with 1 for every element of the main diagonal, upper left to lower right, and 0 in all other positions. So again, it's only for square matrices, so you can see for both 2 by 2 and 3 by 3, that main diagonal is all 1s. Every other element is a 0. So that's what the identity matrix would look like. We are mainly dealing with, or rather only dealing with 2 by 2, just because finding the inverse of a 3 by 3 matrix is a very long process. So we focus on 2 by 2 in Algebra 2. 3 by 3 would kind of be above and beyond what we need to do in Algebra 2. But then what this explains as well is that for any square matrix A of the same dimensions as I, so we're only dealing with 2 by 2 like I said, if you multiply A times I or I times A, because remember the order you multiply matters, so if you switch the order in this case you would get the same answer and it would be the original matrix A. So that's all this is showing. This is not any formula that you would need to memorize. It's not a formula you even need. It's just rather a formula there to explain what this is saying. This is showing the ABCD, that's matrix A, and then this is the identity matrix. So it's showing that if you multiply matrix A by the identity matrix I, or you could reverse that order, I times A, both of those products will just equal your original matrix A. That's all this is showing here. So it's not a formula that we're going to be needing. So we are going to be going through in the first couple of examples determining if the two matrices we are given are inverses. And this is how you determine that. So two n by n matrices are inverses of each other if their product is the identity matrix. So if you multiply two matrices together and you get the matrix I, or the identity matrix, then they are inverses. So then if a matrix A does have an inverse, this is the symbol for the inverse matrix, so it looks like A to the negative first power. And it's that same inverse notation that we use with inverse functions. So it's not A to the negative first power, it's read as A inverse or the inverse of A. But notice then if you multiply A by its inverse, or again flip that order, both products are equal to the identity matrix I. So in order to determine whether two matrices are inverses, for this example, x, y, this is what you would need to do. If they are inverses, you need to find two different products. So you need to find the product x times y, and you also need to find the product y times x, because in general, again, that commutative property is not true with matrices, so if we do flip the order that we multiply, it could change our answer. If both of these are equal to the identity matrix I, then they are inverses. If one or both are not equal to the identity matrix, they are not inverses. So we're going to go ahead, I'll find x times y first. So this is going to review some matrix multiplication with all of you. So I'm just going to rewrite the two matrices so that they're side by side so I can multiply them. And remember, when you multiply, you're multiplying rows by columns. So some of you, I know, when I show this, I kind of always highlighted the first row, the first column. I've seen a lot of students, especially this year, just do this, where they draw a line between the rows in the first matrix and between the columns in the second, so that they know they're looking at the rows in the first one and the columns in the second. Whatever method helps you, you just have to know you're multiplying rows by columns. So I'm going to start out, multiply row 1 by column 1. So that's 3 times 1, first elements multiplied together. That's 3 plus negative 2 times 1 is negative 2. So that first element in row 1, column 1 is going to just be 1. And then I multiply row 1 by column 2. So 3 times 2 is 6, plus negative 2 times 3 is negative 6. Now I'm done with row 1 because I multiplied it by both columns, so now I do the same with row 2. Row 2 by column 1 is negative 1 times 1, that's negative 1, plus 1 times 1 is 1. And then row 2 by column 2, negative 1 times 2 is negative 2, plus 1 times 3 is 3. And then I'll simplify that. So 3 plus negative 2 is 1, 6 plus negative 6 is 0, negative 1 plus 1 is 0, negative 2 plus 3 is 1. So this, as long as you get all ones on your main diagonal and your other elements are zeros, this is the identity matrix I. And if you need to make a note, so anytime you see capital I written, or if you see me write capital I, that means the identity matrix. So I know my first product, I said I had to find x, y. It does equal the identity, so I still do need to check if I change the order that I multiply. If I now multiply y times x, am I still going to get the identity? Because it's possible I won't, so I still have to check. So now I'm going to write matrix y first, followed by matrix x. Multiply rows by columns. So now when I multiply, in this case, row 1 in y by column 1 in x, I get 1 times 3 is 3, plus 2 times negative 1 is negative 2. And then row 1 by column 2 will be 1 times negative 2 is negative 2, plus 2 times 1 is 2. And then row 2 by column 1 is 1 times 3 is 3, plus 3 times negative 1 is negative 3. And then row 2 by column 2, 1 times negative 2 is negative 2, plus 3 times 1 is 3. And then simplify, so 3 plus negative 2 is 1, negative 2 plus 2 is 0, 3 plus negative 3 is 0, negative 2 plus 3 is 1. So I still get the identity matrix. But do take note, even though I did get the same, if you look at the work to get the product, you can see it is different. The work is not the exact same, but you are still getting the identity. So that means x and y are inverses. So it says determine if they're inverses. I can say yes, and now it doesn't ask you to explain, but I want you to understand why, especially if you're looking back at this, to know how you would explain why or why not. So I can say yes because x times y is equal to I, and y times x is equal to I. So because both products equal the identity matrix, I can say that they're inverses. Are there questions on example 1? Just make sure if you find your first product and you do get the identity matrix, you should not stop and say, yes, they're inverses. You do have to go ahead and find the second product. So if we take a look at example 2, this is asking the same thing. Determine if, in this case, P and Q are inverses. So again, I would need to find P times Q and Q times P. So find both products, potentially. So it doesn't matter which one you try and find first. So if I find PQ first, and just letting you know for these as well, thinking ahead to the test, because today, the homework quiz, there won't be another one before you have your test, but this will be on the test. So if you are saying yes or no, I do need to see actual work written out to justify your response as well. So if you're saying when you multiply them that they're equal to I or not equal to I need to see that. So if I go ahead and multiply PQ, rows by columns, first row by first column, so 3 times 1 is 3, plus negative 1 times 2 is negative 2. First row by second column, 3 times negative 3 is negative 9, plus negative 1 times 4 is negative 4. Is this one going to work out? No. So even though, okay, I can see it's not going to work, I'm still going to find what the rest of this matrix is. But I do know it's not going to work because this is not 0. Negative 9 and negative 4 does not make a 0, so I'm not going to get the identity matrix. But if I do multiply row 2 and column 1, I have 4 times 1 is 4, plus 2 times, or negative 2 times 2 is negative 4. And then row 2 by column 2, 4 times negative 3 is negative 12, plus negative 2 times 4 is negative 8. So this product, 3 and negative 2 is 1, negative 9 and negative 4 is negative 13. 4 plus negative 4 is 0, negative 12 plus negative 8 is negative 20. This is not the identity matrix. And all that means then is that these are not inverses. So if I found PQ and I already know this is not equal to the identity, you do then not need to find QP. You could, but it's not necessary because I already know that they're not inverses. So are they inverses? I can say no because P times Q does not equal the identity matrix I. So if your first product equals I, you have to find the second to see whether or not it does. If your first product doesn't equal I, you're done. You already know that they are not inverses. Any questions? on verifying inverses. Okay, so then the next set of examples is actually finding the inverse of a 2 by 2 matrix, and there is a formula for it. You do not have to memorize the formula, but you have to know how to use it. So I will give you the formula. It does say here that some matrices do not have inverses. So not every square matrix will have an inverse. That's important for you to understand. And this is where we're tying in determinants again. So determinants are on your homework quiz today. You can use a determinant to then determine, does a matrix have an inverse? So for a 2 by 2 matrix, it says the inverse of matrix A, and it gives you a formula for how matrix A is set up. So matrix A has elements A, B, C, D. This is the formula for the inverse. So again, A, it looks like A to the -1. That actually means A inverse, or the inverse of A, is equal to, and it's 1 over A times D minus B times C. This denominator here, if you look back at matrix A, if we multiply A times D and then subtract B times C, this is the formula for the determinant of A. So your denominator is really the determinant of your matrix A. So it's 1 over that determinant, and then multiplied by this matrix. And you get this matrix by rearranging or manipulating the matrix you started with. So what you should notice is that the main diagonal in matrix A, the A and the D, those elements get switched. And then the other diagonal in matrix A, B, and C, those elements stay where they are, but they become the opposite. So if they were positive, now they're negative. If they were negative, now they're positive. And then this matrix gets multiplied by whatever this fraction is out front. It does say then A times D minus B times C cannot equal 0. So what that means is if the determinant of A, because again A times D minus B times C is the determinant of A, if the determinant of A equals 0, then A inverse does not exist. Meaning that matrix, if the determinant is 0, that matrix does not have an inverse. So we're going to look at example 3, part A. It says find the inverse if it exists. So before you find the inverse, find the determinant of the matrix that you're given. So I'm given matrix B. I'm first going to find the determinant of matrix B. So this is reviewing determinants that we covered 2 lessons ago. We used them yesterday in Kramer's rule. So the determinant of B, the product of the main diagonal, 3 times -4, that's -12, minus the product of the other diagonal, 7 times 1 is 7. So this determinant is -12 minus 7, that's -19. And now because this is not 0, I can go ahead and find the inverse using this formula. So I'm going to write B inverse. So again, you basically write it. It's B to the negative first. That's what it looks like. Will equal 1 over the denominator of that fraction is your determinant. So that was -19. So 1 over -19. Multiplied by the following matrix. So again, to get this matrix, I'm looking at my original matrix B, and the elements on the main diagonal, so in this case the 3 and the -4, they get switched. So the -4 is going to be in row 1, column 1, the 3 is going to be in row 2, column 2. And then the other diagonal, those elements stay where they are, the 1 and the 7, but they become the opposite. So because they were both positive, now they're negative. So I have -7 in row 1, column 2, negative 1 in row 2, column 1. And again, you do not have to memorize this. You just have to know how to use it when you see it. And that could be helpful to you to just practice problems. That's the whole purpose of the practice, is so you're comfortable with it. So are there any questions? This is not done. You don't leave your answer this way, but are there questions just in getting to this point? All right, so then you actually, this is a scalar out front. It's a fraction, negative 1/19. You have to multiply this by every element in this matrix. Another way to think of this, though, is when I multiply by negative 1/19, I'm really dividing all of these numbers by the negative 19. So what I want you to do here is, one, if you can divide the numbers to get a whole number, divide it. If you divide it and get a decimal, I want you to leave it as a fraction. So either simplify the fraction or, well, for sure simplify the fraction, but leave it as a fraction if it's not a whole number or an integer. So I'm going to have negative 4 over negative 19. The negatives will cancel each other out. And then 4 over 19 is as simplified as we can make it. So that first element is the fraction 4/19. And then I would have negative 7 over negative 19. Again, that'll be positive, and it's already simplified, 7 over 19. And then in the second row, negative 1 over negative 19. Again, that'll be positive, and it's simplified, 1/19. And then 3 over negative 19, so it'll be negative, and 3/19 is simplified. So this is your inverse matrix for that matrix B. And tomorrow we're going to be going ahead and using the inverse matrices then to solve equations. Any questions, though, on the inverse of matrix B? Okay, so then for the second part, here we have matrix T. I included this one just to show you if we start this one out the same way. So to find the inverse, you first find the determinant of matrix T. And again, that determinant, I'm going to have the product of the main diagonal, negative 4 times 3 is negative 12, minus the product of the other diagonal is also negative 12. So if I have negative 12 minus negative 12, that's really plus 12. This is 0. Because this is 0 and you can't have 0 in the denominator of a fraction, this means T does not have an inverse. So I can say T inverse does not exist. You could also say T does not have an inverse, but you need to know that because the determinant is 0, therefore the inverse does not exist.